Hello. So this next section is on arc length and curvature. So we're going to start with arc length, and the defining property, this theorem, tells us that we have a smooth curve, C. So here's our smooth curve. Right? So this will be our curve. And it could be an infinite curve, right? But in this case, we're starting at point A, right? Which we can, well, we can label as a vector, right? From some origin to that point. And then that vector will just be r evaluated at A. And then the endpoint, point B, can be written as a vector r evaluated at little b. So t ranges from A to B. And then, so the curve is given parametrically by this vector valued function. And it could be a plane curve, although I think you have seen that in Calc 2. So this will be a curve in space, right? Again, for t being between A and B. Although A or B, B could be infinity, A could be negative infinity, but then you tend to get curves with infinite arc length. So we're assuming that the arc length here will be finite. Right, so then the arc length S, so we use the letter S, lowercase s, to represent the arc length, is given by this integral here. So it's the definite integral from A to B, and of the magnitude, or the norm, of the derivative of r. Right? And so, I wrote that out explicitly here, right? Because that's what the norm is. It's just the square root of the sum of the squares of the derivatives of the components. Okay? So that's how you calculate arc length. And to be fair, typically not an easy thing to do, given that, the integrand here is a square root. So generally speaking, this is not going to be simple. In many cases, you'll just have to throw this into your calculator, or throw it into Wolfram Alpha, and it'll calculate the integral for you, at least approximately in most cases. But that's, in most cases, that's the best we can do. But let's do an example where we can actually calculate this explicitly. So these tend to be kind of artificial examples where the integral works out where we can actually calculate it by hand. In many cases, even in relatively simple cases, this integral may not even be doable by hand. So just keep that in mind. Okay, so we want to find the arc length of the curve given parametrically by this, right? So this will be a space curve. These are the components, t squared, t cubed, t squared, on the interval where t ranges from 0 to 4. Okay, so we're just going to do this directly, right, using this definition here. Well, this can be proved that this represents the arc length, but for now we're going to just assume that this is our defining property here. So this is how we're going to calculate the arc length. So what do we need? So we need the derivative of r, right? And then we'll need the magnitude of that. So the derivative, fairly routine, right? 2t, 3t squared, and 2t. And then the norm of the derivative will just be the square root of 4t squared plus 9t to the 4th plus 4t squared. And 4t squared plus 4t squared is 8 times t squared. So I think we get, let's see, the square root of 9t to the 4th plus 8t squared. And let's just write it down here. Actually, we can simplify this a little bit, right? We can take out a t squared, right, under the square root, which just becomes a t otherwise, right? T is positive. So we're allowed to do that. And then we just get the square root of 9t squared plus 8. Right, all times t. Okay, so that's the quantity we're going to integrate, right? So the arc length is the definite integral from 0 to 4, right? That's from a to b. And we just have to integrate this norm of the derivative, right? So that's going to be the integral of t times the square root of 9t squared plus 8 with respect to t. And at this point, this becomes a Calc 1 problem, so I'm sure you can all work it out. But okay, let's do it, right? So this is just going to be an ordinary substitution. U will be 9t squared plus 8. So the derivative of u will be 18 times t dt. So we have the t here. We just have to multiply by 18 and then divide by 18 on the outside. And if we do that, let's see, we get 1 over 18 times the definite integral from, so if u is 0, I'm sorry, if t is 0, u will be 8. And if t is 4, I'll get out my calculator now, so u will be 9 times 16, 144 plus 8 will be 152. Right? And then we just have the square root of u du. So that's going to be 1 over 18, and then you'll have 2/3 multiplied by 2/3, u to the 3/2, and that'll be evaluated between 8 and 152. Okay, so 9 times 3 is 27, so this is 1 over 27 times, so 152 to the 3/2 minus 8 to the 3/2. Oh boy, so okay, so let's see here. 1 over 27, so the square root of 152 is 2 times the square root of 38. So that's going to be cubed. So it's going to be 8 times 38 times the square root of 38, right? And then minus, so square root of 8 is 2 square root of 2, so that's going to be 2 cubed is 8 times 2 square root of 2. So I think we can pull out the 8. I don't know why I put a 12 there. That should be a 27. Okay, and then 8 times 2 is 16, so I think we can pull out a 16 over 27 multiplied by, so it's going to be the square root of 13,718, whatever that is, minus the square root of 2. So I think this is approximately 68.57. Yeah, just making sure. Okay, so I think that's it. So that's the arc length, right? So that's essentially the length of the curve, right? So it's about 68.5 units. I'm not even going to attempt to graph this curve, although it shouldn't be that hard because it's just, you know, t squared and t cubed. But yeah, it wouldn't look, it just probably wouldn't look good the way I would do it. So, all right, so again, this was doable by basic substitution. You'll see that in most cases that's not usually likely. Right. So going back to this definition, what I would like to do is imagine you have a curve where the starting point is fixed, right? Starting point, point A is fixed. But then the curve can just keep going, right? So we can end it somewhere, but that endpoint is variable, right? So suppose that the curve just keeps going, but at some point we end it at this point here, so let's say this is r of t, right, where t is the parameter. Right? T could be for time. So r of a will be fixed, but then t could be variable, right? So in that case, the formula for arc length, well, arc length will then depend on t, right? So then the formula we get is s as a function of t will be the definite integral from a to t of the magnitude of r prime of, so now we need a different letter here. I guess we'll use u as our dummy variable, right? So yeah, the picture here is that you have a curve where the starting point is fixed, but then, you know, at the ending point, well, we can end this anywhere, right? So in other words, right here will be our r of t, right, as a vector from some origin, let's say. Right, so imagine there's an arrow from the origin, the 0 vector, to that point. Okay. Yeah. So as t moves along, right, the arc length just gets bigger, right? I mean, we're presuming that, right, because the magnitude is going to be positive, that the integral will then be positive. So, right, so of course that this s of t will just be some positive number, or at least non-negative, right? And it's also an increasing function, right? Because as time goes on, you can only get longer, right? The arc length can only increase. So that's the idea, right? So this piece here will be s of t. Right. So I just mentioned that it's an increasing function. How do we know that? Well, we could just take the derivative, right? We could take s prime of t, or ds divided by dt, right? And just by the fundamental theorem of calculus, or I think the second fundamental theorem of calculus, depending on which book you use, this is just going to be the magnitude of r prime of t, right? Which of course is positive, right? So there you go, right? The rate of change of s, the rate of change of the arc length, is simply the magnitude of the derivative of r. Right. We've seen that before, right? Remember, this is just the speed. This is how fast you're going. So again, back to this curve here, right? As you're moving along the curve, right, the rate of change of the distance that you're traveling is how fast you're going. It's your speed, right? So yeah, it's at any given point, how quickly you're moving, right? Your speed is just given by this quantity here. Right, so it's the rate of change of the arc length, right? And in this case, we call s, right? S is the arc length parameter. Right? And the idea is that we can reparameterize our curve. Instead of, right, having r depend on t here, we can have it depend on s. Right? As a practical matter, that's usually very difficult to do, but we're going to do an example where it is possible and where it kind of makes sense, right? Yep. So here's the example I have in mind, right? We're given this this plane curve, r of t, so it only has two components, 12t and 5t, for t being between 0 and 1. We want to find r as a function of s, not as a function of t. Okay? Yeah. So, in fact, I just called this a curve just a minute ago, but this isn't even a curve. It's just a straight line. Right. So here's x, here's y. Right. When t is 0, you're starting at 0, 0. Right. And then when t is 1, you're at x is equal to 12, y is equal to 5. So this is your endpoint. And in between, This is just a straight line, right? So it's a straight line segment, starting at 0, 0, and ending at the point 12, 5. Okay. So, right. So how do we find, first of all, the arc length parameter s? We'll do this in yellow. So s of t is just going to be the definite integral from 0 to t, right? So we're starting at 0, and t is going to be between 0 and 1 of the magnitude of r prime of t. Oh, yeah, I can't use t, right? Because we're using it as our upper limit of integration. So we'll go back to u. Right. Right. But it's not going to matter here, right? So what is r prime of u? Well, it's just 12, 5, right? So it's a constant vector. After all, r prime of u is just the velocity, right? So you're just moving with constant velocity, and so therefore constant speed. What is the speed? Well, square root of 12 squared plus 5 squared. And so you get the square root of 169, which is 13. So there you go. You're just integrating from 0 to t of the constant, the number 13. Right. So you just get 13t minus 13 times 0, so you just get 13 times t. Okay, so that's s of t. It's just 13 times t. Right. So s of 0 is obviously 0. You haven't gone anywhere yet. And then where you end up is when t is 1, you just get 13. So the arc length of this curve is 13. Right? I mean, we don't think of it as arc length, we just think of it as the length of the line segment. Right? So its length is 13. Right? So now I'm going to take this expression here, right? Yeah, so this expression is s is equal to 13t. We know it's a function of t, right? And I'm just going to find the inverse. In other words, I'm going to solve for t here, right? So t then is obviously just s divided by 13, right? And now we can rewrite the function r of t, which was 12 times t for the first component, 5 times t for the second component, and just replace t with the expression s over 13. Right? So if I do that, I get r of s. It's going to be, well, 12 over 13 times s for the first component, and 5 over 13 times s for the second component. Okay? Yeah. And of course, remember t ranged from 0 to 1, but now s ranges from 0 to 13. Right. Again, how did I get the 13? I just plugged 1 into the arc length function, s of t, right? So yeah, s varies between 0 and 13. All right. So what have we gained by doing this, right? I mean, we were given r as a function of t, right? 12t for the first component, 5 times t for the second component, and we simply rewrote it in terms of s instead of t. So yeah, so what have we gained? In the original picture here, right, when you have this position function, this is the position of some object starting at 0, 0, and then it moves along this line, right, all the way until it gets to the point 12, 5, and then it stops, right? And so to go from one point to the other, it took essentially 1 second to go that entire distance, right? On the other hand, if you, oops, can I erase that? There we go. Right. Instead, if you consider moving, right, with r of s, s being the arc length parameter, right? Instead of taking 1 second, it now takes 13 seconds, which is a long time. I'm not going to take 13 seconds to get there, but right, it would take 13 seconds. In other words, you're moving, right, at a constant speed again of 1, right? And we can check that, right? If you take r prime of s and take its magnitude, you just get 1. Okay. So in the original picture, our speed was, right, 13 units per second, right? 13 units every second. And in the picture for r of s, right, you're moving at 1 unit per second. Okay. So, yeah, so that's, right, we've taken a constant speed of 13 and reduced it down to a constant speed of 1. So, all right, so that's really all we've gained in this picture here, right? But to do this for more general curves, I mean, we could do it for a circle maybe, but to do it for more general curves of different shapes, it's going to be much more difficult, if not impossible. So I wanted to do an easy case where we can illustrate that at least, you know, hypothetically, we can reparameterize in terms of s as opposed to t. And by doing that, you simply are looking at the geometry of the curve, or the line in this case, rather than a particle moving along the curve at varying speeds, or in this case, a constant speed. Okay, so let's summarize this with the following theorem. Okay, so you have a smooth curve given parametrically by r of s now, where s is the arc length parameter. Then, right, the magnitude of the derivative of r with respect to s has to be 1. Okay, and it works the other way too. If the magnitude of r prime of t is 1, the only way that can happen is if t is the arc length parameter. So you might as well call it s in that case, rather than t. Okay, so the point is, right, you have your curve C, and if it's expressed, if the position is expressed in terms of s, the arc length parameter, you're moving at a constant speed of 1 unit per second, right? Or, you know, per unit of time. Right? In other words, your speed is not changing, right? So it's not like you're starting slow, speeding up, and then slowing down again, and then speeding up, right? Your speed does not change, right? It might change with respect to t, but not with respect to s, right? So your speed is a constant, and that constant is just going to be 1, right? So that's the idea here. So going back to what we did in the previous video, remember we had this unit tangent vector, which could change with respect to t, right? So we just had a vector pointing along the curve at each point. They all have length 1, right? So the lengths of the vectors are not changing, although they look like they are kind of, but, right? So we can reparameterize that in terms of s, right? So the advantage of that is it doesn't matter how fast we're moving, right? We're changing it to a constant speed. And now, right, as t is changing, remember, t is a unit vector, so it's not changing its length. It's only changing its direction, right? So if we take the derivative of this function, right, we take t prime of s, that tells us how quickly the direction is changing, right? And in what direction it's changing, right? So it's going to be pointing normal to the curve, right? It'll be orthogonal to t. So how quickly, right? So we don't care what direction it's changing. We just care how quickly it's changing. So if we take the magnitude of that, that gives us an indication. It gives us a numerical quantity. It's a number. It's a scalar of how quickly, right, the vector is changing direction, right? and we give this a name. We call it k. K is for curvature. If you're wondering, why don't I use c? Well, remember, we're already using c for just the name of the curve. So I don't want to get confused with curve and curvature, right? So yeah, so this is the definition of curvature, right? Curvature, k, and it's just a number, is just the norm or the magnitude of the derivative of t with respect to s, right? Not with respect to t, with respect to s. Okay, right? So maybe this is not the best picture here. So let me draw another curve. How about something like this? Right. And you can see at this point right here, if you can draw your unit tangent vector t, at a very nearby point, we can draw another unit tangent vector. And you can see that the direction is not changing very much, right? The original one might be here. Let's call this T1 and T2. And the new one might be here, right? So T1 and T2, right, the direction is not changing very much. Okay? On the other hand, if you go over in this direction here, if this is my point for T1, so this is the vector for T1, and then again, I just move a little bit to another point, to a neighboring point, and now I take the unit tangent vector. Look how much it's changed. Look how much the direction has changed. Right? So curvature is simply a measure of how quickly the curve is curving. Right? I mean, so over here, with these T1 and T2s, it's not curving very much. It's almost pretty straight, right? So that it would be a very low curvature here, right? So this is a low curvature, right? But then over here, where the unit tangent vector is changing direction significantly, this would be a high curvature. Make sense? Right? And if of course, if you just have a straight line, right? You have your unit tangent vectors. They all point in the same direction, and they certainly don't change length. So in that case, the derivative of t would just be the 0 vector. And of course, the magnitude of that would be 0. So we just showed that for a straight line, the curvature is 0. Well, if it's a straight line, right, it's not curving. There's no curvature. So that should make sense, right? Okay, so that's the definition of curvature. Okay, so here it is again, just for reference, because now we're going to use this formula for curvature to calculate the curvature of something very familiar to all of us, right? The circle. So we parameterize the circle with little r of t. It's equal to capital R times cosine of t times I plus capital R times sine of t times j. So capital R is a constant. Right? Capital R is just, well, the radius, right, of the circle. So capital R is for radius. Little r is the position function, right? So that's the vector at each point coming from the origin, right? So yes, r of t is obviously changing as you're moving along the circle. In this case, counterclockwise, right? All right. So yeah, this is not going to be an easy calculation, but let's see how we can do this, right? So what do we need? We need, first of all, we have the position function r of t, right? And we need the unit tangent vector, right? But we need it in terms of s. So before we go any further, can we write r as a function of s? Right? So that's our first step here. And yeah, so to do that, let's just find r prime of t. So the derivative of the position, which is the velocity here, right? It's just going to be negative r sine t times I plus r times cosine of t times j. Right? And the magnitude of that, right, so the speed, the derivative, the magnitude of the derivative, right, the norm of the derivative, is just going to be the square root of, so negative r sine t squared plus r cosine t squared. And I hope you see where this is going. You can factor out the r squared, and you just get sine squared plus cosine squared, which is 1. So the square root of r squared is r, right? So the speed is r, right? It's a constant, right? So yeah, it turns out not only to be the radius, but also the speed, right? And remember that this is also the rate of change of s with respect to t, right? So the derivative of s, the arc length, with respect to t is just r. Right? So if I integrate, right, I just get s, which of course is just r times t. Right? And now to solve for t, we just divide by r, right? So t is s divided by r, capital R, the radius, right? So yeah, so now that we've rewritten t in terms of s, we can replace all the t's with s over r. So r of s now is just going to be capital R, the radius, times the cosine of what used to be t is now s over r, right, times the unit vector I, plus r times the sine of s over r times the unit vector j. Okay, so this is still the position vector, but written in terms of the arc length parameter s rather than t. So, right, so we did this for a straight line. Now we just did it for a circle. But you know, trying to do this for more general curves is not going to be this simple. In particular, this relationship between t and s, you know, where you're just multiplying or dividing by a constant, is not usually the case. Okay, well, now that we have the position, we can find the velocity, right, just by taking the derivative. So the derivative of r with respect to s now, or r prime of s. So, right, so it's almost as simple. We just need the chain rule here. So we're going to get the derivative of cosine is negative sine of s over r times 1 over r. So you can see that the r's cancel. Right, so negative, well, let me put the negative in front. Negative r over r times sine of s over r times I. And then same thing here, plus r over r times cosine of s over r times j. Again, the 1 over r comes from the chain rule. So this is really just negative sine of s over r times I plus cosine of s over r times j, right? And so if we take the norm of that and get the speed, right, we get the magnitude of the derivative of r with respect to s. Well, you just get the square root of, right, negative sine squared, right, plus cosine squared, which of course is 1, right? But we already knew this, right? Remember, the magnitude of the derivative of r with respect to s has to be 1. That was that theorem that we did earlier, right? Okay. So now it shouldn't be that hard to get the unit tangent vector, capital T, right? Capital T with respect to s, it's going to be, well, r prime of s divided by the magnitude of r prime of s. Although we don't, right, we know the denominator is 1, so this is really just r prime of s. Right? And so that's another advantage of reparameterizing in terms of s instead of t, is that, right, the unit tangent vector is just going to be the derivative of r. But with respect to s, if it's with respect to t, then the denominator will probably not just be 1 anymore, right? So, and we already calculated this, so I can just copy it down again. Oh no, we did, yeah, we did, yeah, that's r prime of s. Got it. Okay, so that's negative sine of s over r times I, right, plus cosine of s over r times j. Okay, so that's the unit tangent vector. Right, and we already know it's a unit vector because its magnitude is 1. Right. Okay, so the only thing that's changing about t, of course, is the direction. Okay, so what do we need for curvature, right? Remember, curvature is the derivative of t. So now we need the derivative of t, right, with respect to s, or if you prefer, the dt over ds, right? And that's not hard. It's just the derivative of negative sine is negative cosine, but by the chain rule, we get a 1 over r, right, times I. And then the derivative of cosine is negative sine, so we get minus 1 over r times the sine of s over r times j. And in fact, that should look familiar. That's just r, but divided by, instead of multiplying by r, you're dividing by r. Right. So essentially, we can just factor out this negative 1 over r here and multiply by cosine of s over r times I plus sine of s over r times j. All right, one last thing we need to do, right? Remember, the curvature is not a vector. This is a vector down here with the i's and j's, right? The curvature is just the magnitude of that vector. So now we take the magnitude. So k will be the magnitude of the derivative of t with respect to s. Right? So when you take the magnitude, you just get 1 over r, and then times the square root of, well, cosine squared of s over r plus sine squared of s over r. So of course, that's just 1. So 1 over r times the square root of 1 is 1 over r. And that's it, right? So the curvature, k for curvature, right, is just 1 divided by the radius. It's the reciprocal of the radius. Okay. So for a circle, right, the curvature, k, is just 1 over its radius. And that should not come as a surprise, right? Let's think of a circle with a very small radius, and then we think of a circle with a very big radius. Or I can do a little bit better, I hope. I don't go quite as quickly. All right, not great, but it's a circle, more or less. Right, so here you have a really tiny radius, right? R is very small. And here we have a very large radius where r is very large. So remember, intuitively, while we think of curvature, right, if we take a small piece of this, right, in other words, we're going, at a constant speed here, speed of 1, right, if we look at this piece here, right, it's rather straight. I mean, it is a part of a circle, so it is curved, but not very much, right? On the other hand, if you take the same length, the same arc length here, right, so the same distance, you get a piece that's much more curved, right? So when r is small, k is large, right? You're curving quite a lot. But when r is large, right, k is small. Okay, so for a big circle with the large radius, right, as you're moving along, you are curving, but not very quickly. Right, you're almost moving in a straight line, but just ever so slightly you're curving, right? As opposed to the little circle here where you're curving very quickly. You're just going around very, very quickly, and it's a large curvature. So intuitively, I think that makes perfect sense. Right? In fact, r, the radius then, is just 1 over the curvature. In fact, we call r the radius of curvature. Let's spell radius. Right. And so for, I think I drew a curve something like this earlier, right? And you can see where the curvature is large and where the curvature is small, right? So imagine at a given point drawing a circle with this sort of the same, well, the same curvature at that point. It'd be a very large circle here. On the other hand, if you drew a circle over here, right, it would be a very small circle. So again, the curvature is large, the radius is small. When the curvature is small, the radius is large. Okay, so not a surprising result for either the radius or the curvature, which is just the reciprocal of the radius. Okay, so that was again a rather tedious example to get there. There was a lot of calculation that we had to do for a result that we probably could have almost guessed that was going to be the case. And again, this is just going by the definition of curvature, right? There's going to be much easier ways to calculate the curvature than to use this definition, because this is an awful way to calculate curvature in practice, right? It worked for the circle, right? And it works for a line. It doesn't work very well for, say, a parabola or an ellipse or some other generic-looking curve, like this one down here, right? Very difficult to calculate the curvature in general. Okay, so again, at the top here we have the definition of curvature. But suppose you have a curve, right, given parametrically. So here's your curve C again. But let's suppose it's given with r as a function of t, some general parameter, let's say time, not in terms of s, right? So yeah, so how would we calculate the curvature? Well, ordinarily we'd have to convert that to r of s and then take the derivative and the tangent vector and all. That's what we did for the circle just now. But it turns out there's an easier way, right? You can just use this formula here, right? Just take the derivative of the unit tangent vector t, right, as a function of t. The drawback is you have to divide by the magnitude of r prime of t then, right? So yeah, much easier to use this formula here, this one here, than to do it the way we did it for the circle. Oops, sorry about that. Okay. So yeah, and in fact, you don't even have to calculate the unit tangent vector or its derivative. You can also just use this formula here, which is in terms of the derivative of r and the second derivative of r. Remember, the derivative of r with respect to t is just the velocity, and then the second derivative is just the acceleration. So when you have your position function, it's fairly routine to calculate the velocity and the acceleration, and then that's all you need, right? So you take the magnitude of the cross product, right, of the, so this was acceleration. So you take the magnitude of the cross product of the velocity and the acceleration, and then divide by the magnitude of the velocity cubed to the third power. Okay. So yeah, in practice, this is a much easier way to calculate the curvature of any, any curve. And this could be a curve in a plane or even a curve in space. Or if your curve is given in the plane, it's a plane curve, right? And in fact, let's suppose you have a curve that's given as the graph of a regular function, y equals f of x, right? Then there's an even easier way to calculate the curvature. It's just this formula here. It's the absolute value, right? This is not magnitude because, right, this is a regular function. It's not a vector function, right? So y double prime is just the second derivative of the function y. And if it's negative, just make it positive, right? So curvature by its definition will always be positive, right? It's just the magnitude of, well, yeah, it's the magnitude of a vector, which is positive, right? Or at least non-negative, I should say. So, yeah, there are some books that would explain when curvature could be a negative number, but I find that confusing. So luckily, this book doesn't do that. So here, curvature is a positive number, right? So that's why you take the absolute value. Right. Anyway, so that's the formula. So it's the absolute value of y double prime divided by 1 plus y prime squared, and then all to the 3/2 power. Right. So that's if your function is given, well, that's if y is a function of x, right? But even if you can't write it as a function of x, you can write it possibly parametrically, where x is a function of t and y is a function of t. And in that case, you can write it using the second formula here. Right? So it's the absolute value of x prime y double prime minus x double prime y prime all over, and then it's the, to the power 3/2 x prime squared plus y prime squared. Okay, so, right, so 4 very good formulas for calculating curvature, without using the definition, which is probably the worst way to do it. So each of these ways would be easier than this way here, right? Right. So yeah, let's just do a quick example. Okay, so find the curvature of y equals x squared. You know what that is, right? That's just your usual parabola. Okay, a bit sloppy, but you get the idea, right? At the point 1, 1, so that's right around here. And then again at the point 2, 4, way up here. You can see that. Right, so yeah, I think the easiest way to do this is to recognize that this is just an ordinary function of x. So that's the graph of the function. So we might as well just use the very first formula here. So what do we need? We need both derivatives. The first derivative is just 2x, and the second derivative is just 2. So k, right, which is, again, in absolute value, y double prime, over 1 plus y prime squared to the 3/2 power. So plugging in y double prime is 2, so the absolute value of 2 is, of course, just 2. And then the denominator will be, let's see, 1 plus 2x squared, the whole thing squared, to the 3/2 power. So you get 2 divided by, well, 1 plus 4x squared, all to the 3/2 power. Okay, so that's the curvature at any given point, right, in terms of x, right? So this is a function of x. I'm just copying it down. Right, so they're asking for 2 specific values of x, right? X equals 1 and x equals 2. So let's just start with x equals 1. You get 2 divided by 1 plus 4 times 1 squared. So 1 plus 4 is 5. So we get 2 divided by 5 to the 3/2 power, which is 5 square root of 5, right? So that's approximately 0.1789. Okay, 0.1789. Close enough. Rounded to 4 decimal places. Right, and then at the point 2, 4, so x is 2 now. So plugging in 2 for x, you get, again, the same 2, divided by 1 plus 4 times 2 squared. 4 times 4 is 16, so 1 plus 16 is 17. So this will be 2 divided by 17 square root of 17, which is approximately, my calculator says 0.0285. Okay. Right, which is considerably smaller. And just looking at the parabola, right, you can see that even at the point 1, 1 here, right, it is curving, but it's significantly less than 1. It's even less than 0.2, right? And then at the point 2, 4, the curvature is even less. Right? So where do you think the curvature is the biggest? Probably at the vertex, right? Probably at 0, 0. In fact, right, what happens when x is 0? Then the curvature is just 2. So 2 is the biggest you can get at the vertex at 0, 0. Of course, you can prove that by maximizing the curvature function, right? Take its derivative, set it equal to 0, find the critical numbers. You know, this is what you did in Calc 1. So yeah, we didn't prove that, but just looking at the graph, intuitively, this makes sense that this is the maximum curvature of the parabola. Oops, sorry, maximum curvature of the parabola. Right, is at the vertex at 0, 0. Right, and of course the radius of curvature there would just be 1/2. Right, so if you were going to draw a circle, and I drew the circle wrong up here. So yeah, so the circle would be a very small circle of radius would be 1/2, or I should use capital R, right? Right, so makes sense. It coincides with our intuitive notion of what curvature is, and it's but it's good to calculate it using one of these formulas here, right? So I hope that helps. Okay, so one final property here. Suppose, right, that we have a vector-valued function, r of t, and let's suppose that it actually represents the position of a particle moving along the curve c, right? So it's a position vector, right? Then we can calculate its acceleration, a, right? So a is the acceleration vector, and it can be given by this formula here, right? So it's the second derivative of s. Remember, s is the arc length parameter. Right, so second derivative of s times the unit tangent vector t, capital T, plus k is the curvature of the curve, right, times the first derivative of s, right, squared. So that's the speed squared, times the normal vector, the principal unit normal vector n. Okay. So again, this is probably a good thing we want to prove here. So I'm going to prove this. And probably not something I would ask on a test, right? If I ever ask for a proof, it'll be a very short, maybe 1 or 2 lines. This one is not. This one's like 4 or 5 lines. So, all right. So let's start with what we talked about in the previous section, the previous video, was that the acceleration was given by this formula here. So it's the tangential acceleration times the unit tangent vector t, plus the normal acceleration times the unit normal vector n. Right. So you see where this is going, right? Essentially, this represents the tangential acceleration, and this will represent the normal acceleration. Okay, so that's where we're going here. So remember what the tangential acceleration is. It's the derivative of the speed, which is the magnitude of the velocity. Right? Yes. Oh, and we're only taking the derivative of the speed. We're not taking the derivative of the t here, right? Okay. Plus, and then for the normal acceleration, we had this formula. It's the magnitude of v, right, times the magnitude of the derivative of the unit tangent vector. Again, this is now with respect to t here, with respect to time, right, times the normal vector n. Okay. But remember what the magnitude of v, right, is just the derivative of s. It's the speed, right? So here, if we want the derivative of that, right, then we just take the derivative of the speed, which is the derivative of s. Right? So of course, that's just the second derivative of s. Right. Times the unit tangent vector t. Okay. So the magnitude of v, of course, that's just the derivative of s. And the magnitude of t prime, right? So remember what t prime is, right? Well, we had this formula for curvature, right? Remember the curvature was the magnitude of t prime, right, divided by the magnitude of r prime. Again, with respect to t now, right? And of course, the denominator is just the magnitude of the velocity, v. Right? So if I multiply by the velocity, the speed, then I get the magnitude of t prime, right, is just equal to k times the magnitude of v, the speed. Okay, so I have the derivative of s, and then the magnitude of t prime is going to be k times the magnitude of v, which again is the derivative of s, right, times the normal vector n. So there you go, right? The derivative of s times the derivative of s is just the derivative of s squared. So I'll put the k in front, and then the derivative of s, which is the speed, squared times n. And that's all it is, right? So that is just another version of the acceleration, right? So there you go, right? The tangential acceleration is just the second derivative of s. If you think about it, it's just the derivative of the speed, right? And speed is just the first derivative of s, right? And, right, so the normal acceleration can also be calculated by the curvature times the first derivative of s squared, right? So in other words, the speed squared. Okay? And before we go, I just want to bring this back to one example we did earlier, right? The circle, remember, of radius capital R, right? Remember that the curvature k was just the reciprocal, 1 over r. Okay? So in that case, right, we can write the acceleration, right, as k times, or the normal acceleration, I should say, right, k times the derivative of s squared, right? But if k is 1 over r, right, and the derivative of s, we did that up here, right? The derivative of s is the magnitude of v, which can I just write as, you know, v as a scalar, right? So this is just v squared, the speed squared. Well, right, so that's just v squared over r. And for those of you who have had physics, you recognize this as the centripetal acceleration. Right. Again, for an object moving along a circle. Right. So yeah, so that should help explain this formula here. If you think of something moving along a circle, the curvature, k, is just the reciprocal of the radius, so that's the 1 over r, and the derivative of s is just the speed. So the speed squared divided by r, right? So, yeah, so there you go. Hopefully that makes a little more sense now, relating it to the usual formula that you get in physics for centripetal acceleration. Okay, so I hope that helps, and that should do it for this section and this chapter. Yeah, so again, all these formulas that we've been writing down up here, all these formulas, they're all on your formula sheet, right? So you don't have to memorize any of these. Just you know, refer to the formula sheet if you need them on a test. Okay? Good luck.